presentation, but they are described in the white paper that's associated with the presentation. When the victim browser needs to send data back to the attack server, there's two methods. If it's a small amount of text data, that can simply be sent in an image request. The payload on the browser creates a new image object, sets the source to the controller script on the attack server, and the data is just sent in the URL query string. And once the image is appended to the document body, the browser will automatically process it, and the attack server doesn't even have to send an actual image as a response. If it's a larger amount of data that won't fit into a URL, or if the data is binary and the attacker doesn't want to encode it for some reason, then it can be sent using an HTML form. Excuse me. The data is put into an input text box. The action is set to the controller script on the attack server, of course. The method is post. And the target is set to an unused iframe so that when the form is submitted, it won't redirect the web page to to the action. XML HTTP request is an object in the HTML document object model. It pretty much allows JavaScript to create its own arbitrary HTTP requests, usually either GETs or POST. It's best known for being the key component in AJAX sites like Google Maps or Yahoo Mail. Normally, it can only transfer text data because, as the name implies, it was designed for XML content. Thank you to Marcus Granato for documenting how binary data can be transferred by changing the character set to X user defined. I have no idea how he figured this out. Unicode seems to be a rather esoteric implementation of Unicode or use of it. But without that technique, it wouldn't be possible for the attack tool to retrieve binary files like images or PDFs and whatnot. One more other thing real quick. It's important to remember that XML HTTP requests can only be used to contact the origin server. Otherwise, it would be a huge violation of the same origin policy. Because of that, or rather I should say, once the DNS pinning switch has occurred, the victim server is considered origin by the browser, which means that XML HTTP request cannot be used for communicating back to the attack server. And that's why those earlier methods are required for the command and control functions. This is a representation of the demonstration environment. It's fairly typical for a corporate network. The internal network uses private IP space. There's a firewall separating it from the internet. No inbound connections are allowed from the internet. The only outbound connections are on web ports for all hosts and on DNS for the resolving DNS server. There is a Linux server that's running a simple web application with a MySQL backend. There's a Windows server that is running file sharing and also acts as the resolving DNS server internally. And then finally, there's a victim workstation, which is running Windows XP, is fully patched, at least as of a couple of weeks ago it was, with a fully patched version of Firefox. And the user is running with non-administrative rights. So just to emphasize, this isn't using any patchable vulnerabilities. This is just standard browser behavior. On the internet side, there's a fictional popular website that has been infected with cross-site scripting by the attacker. As I'm sure Jeremiah and Robert will mention in their presentation, these are a dime a dozen. Google, Yahoo, all the big names have had problems with cross-site scripting at some point. The attack server, we already talked about those components, and of course, there's the attacker's workstation. From a physical point of view, it's implemented on two laptops connected by a firewall running DDWRT. Each laptop has multiple virtual machines. Thank you to my colleague Eric Dupre, who gave me some assistance in setting up the firewall and some of the VMs. So I know I've already gone over anti-DNS pinning from a higher level, maybe even a medium level, but I want to go over it again in more detail. It's a fairly complicated attack for web technologies, at least, so I think there's some benefit in this. Of course, it starts off with the victim browser going to a site infected with cross-site scripting and downloading a small piece of malicious JavaScript as a result. The JavaScript will cause the victim to load a new page from the attack web server. Now, in a real scenario, this would probably be in perhaps a pop-under window that's small or an invisible iframe. There are a number of techniques for hiding the new page from the user. In my presentation, I'll be showing it in a large window so that debug statements can help narrate the attack flow. Jeremiah and Robert might be going over some of the techniques for hiding content in their presentation. The base attack page is pretty simple. There's a JavaScript that using set timeout causes a new script tag to be appended to the document every second and a half. And as I mentioned earlier, it just points at the controller script asking for a new command. On the first time that a browser polls the attack server, the controller script will insert a record of the session into the database so that the session appears on the attack console. Every poll causes the controller script to look for new commands in the database for the victim browser. Anything that it finds is sent back to the victim browser in JavaScript statements. Now, at this point, the attacker can start probing the victim's network using a number of different techniques. Port scanning, perhaps doing some keystroke logging from the victim. We're going to skip this stage. We're going to assume that the attacker has already performed reconnaissance and has identified the Linux server as a website that he's interested in. So the attacker starts up an HTTP proxy service on the attack server. And when the attacker's browser sends a request to the proxy server, it checks to see if it has seen any other requests from going to that same IP address and same port number. If it hasn't, then it knows that it needs to start up the foundation for a new anti-DNS pinning attack. The first thing it does is create a random host name and DNS record that points at the attack web server's secondary IP address. Actually, let me stop for a second. Something I forgot to mention. The reason it's important that there's a secondary IP address is that when the firewall rule is set up to simulate a web server outage, it's important that command and control functions still be available through the primary IP address. At the same time, the proxy server creates a command that tells the victim browser to create a new iframe and point that iframe at the controller script on the random host name. And the query basically says, give me a new attack payload for anti-DNS pinning. Once the iframe, or once the payload completes loading in the iframe, it sends a message back using an image request to the attack server saying, okay, I'm ready. The payload's done. You can set up the firewall rule. So the controller script creates a firewall rule to simulate the web server outage and changes the DNS record as well. At the same time, the payload on the victim browser retrieves the next URL that it's supposed to be processing and creates an XML HTTP request object associated with that payload. So the web browser will start to process that object and will fail because of the firewall rule. Now, this is not entirely accurate, but it's a bit of an oversimplification, and in my presentation I'm not going to go into the details why, but if you want to know, email me and I can explain it. Essentially, once the pinning expires in the browser, it will dump its cache and requery the DNS server. This time, of course, the DNS server will respond with the IP address of the victim host. The iframe, as soon as this happens, the iframe payload sends a message back to the attack server saying, okay, we're done. I have the victim's IP address pinned in my cache. You can drop the firewall rule, and we're going to proceed with the attack. The browser processes the XML HTTP request, and this time it will connect to the targeted web server, since that's what's pinned in the cache, and get a response, forward it back to the attack server. The controller script inserts the response into the database. The whole time, the proxy server has been polling the database, looking for the response to that original request that the attacker sent. As soon as it sees it, it returns it to the attacker's browser, and of course, it's displayed. So I'm sure that is clear as mud. Let's get started with the demonstration, the first demonstration. All right, this is the attacker's workstation, and this is the victim's workstation. We'll start off by having the victim go to a fictional website, already been attacked. This looks like an interesting link. User clicks on it, and has been redirected to a malicious website. Now, of course, as I mentioned earlier, this would be invisible to the user in a normal scenario. If we switch back to the attacker's browser, we can refresh the console and see that it has identified the session. We can run arbitrary JavaScript at this point, which will appear on the victim side. And clear that out. There we go. So at this point, we can start up the HTTP proxy service and confirm that the browser is configured to use it. That's the primary IP address on the attack server. And we can browse to the IP address of the previously identified web server. If we go back to the victim browser, you see that a new iframe has been created. This is the random host name. This is for just HTTP. Now at this point, the DNS record has already been changed and the firewall rule has already been created. It's pausing for a bit, waiting for the pinning to time out in Firefox. While we're waiting for that, I can show you a little bit more detail on the polling. This is the victim browser polling for new commands. Most of these are going to be empty, but this one should contain some data. Basically, a command telling the browser to create a new iframe, pointed at the random host name, the controller script, and asking for a new payload for the anti-DNS pinning. The browser should be pretty close to switching over. Let's see here. Well, should be. We'll wait just a few more minutes, a few seconds. Well, that's not good. It's usually a lot faster than this. Now, you'll notice that Firefox is hanging while it's timing out. That has to do with being aggressive at reconnecting to the victim web server. It's possible to make it a little slower so that the browser is not hung and the user doesn't notice anything. All right, it's getting resets back. Here we go. Okay, good. So this is the iframe that's being used to post back data to the attack server. Here's the content that is being posted. It's basically just a URL encoding of a HTTP response. Switching back to the attack server, we see that, or the attack workstation, it's found a fairly primitive web application that the attacker can start interacting with and get some data back from. Attacker can start looking to see if it's vulnerable to common website vulnerabilities. Which it is, not surprising. And given the quality of it, I'm sure it's vulnerable to SQL injection, which we can test with a quick tautology, and it is. So looking back at the victim browser, you can see the requests as they were coming through different URLs. So at this point, the attacker could continue looking at this application, or probably go on and look for something more useful. Now, there's something that I didn't mention that if you're paying close attention, better switch back. You may have noticed. Because XML HTTP request can only connect to the origin server, and because the origin server has to be in an attacker-controlled domain for the switch to work, when XML HTTP request contacts the victim server, it's going to be seeing a host name and a domain name that's completely alien, which means that for most web servers, only the default website will be responding to these requests. This has led some people to suggest